Hi guys, Andrew here from Polo Reef and Jonathan Hale from Polo and Country Critters. Today will be our first attempt to do an extreme walkthrough, detailed filtration, computer lighting walkthrough of the whole system and process. Jonathan, why don't you tell us a little bit about the materials and how they came and were put together and the problems we had after that.
The dimensions of the tank are 15 feet front to back, 15 feet left to right, a total depth of 9 feet with the window being 7 feet of that, 2 feet below grade. The 2 feet that are below grade are not acrylic, it's a FRP pan that the window sits in. That actually came in 2 pieces. The front half and the back half attached to the back wall, because the back of the tank is also FRP. We had to bond that. First, getting it into the house through an old garage door was a challenge with cranes and forklifts to maneuver everything into place. We then had to laminate those two together. And then the window, which is 4 inches thick of Reynolds acrylic.
This is all Reynolds.
Came as a U-bonded structure.
On a truck.
Which moving it itself was very challenging because any twist or misleveling would crack it because it was already bonded as a U. So that goes into place into the bottom pan, and then there's a 2-piece top structure that had to be bonded together that holds the window in place from bowing and also attaches it to the back. So the main returns from the tank are provided by a 3-inch return in each corner of the tank, as well as computer controlled 2 6-inch valves that open and close at as most random schedule as we could develop, with it still being random. Flowing through those pipes is approximately 600 gallons a minute.
That helps with the flow coming down the back.
This way. We also have just 2 sea swirls that we added a little later on here. They're 1.5 inch sea swirls that come off the main pipe. Andrew had us add those after the top was so clear you were able to see up through to the ceiling. So these just add a little bit of surface agitation so that you can't see the lights through the top of the tank, through the water surface.
What's any gallons per minute going through there?
So on the closed loop, it's approximately 300 gallons a minute. On the open system that runs down to the sump, right now we're flowing about 600 gallons a minute.
Right.
With capabilities of flowing higher than that, but we feel that this has been our sweet spot.
And then if you add in the sumps and stuff like that, you're talking about 1,100, 1,200 gallons per minute through the system.
Yeah.
Per minute.
So even with all the flow we had from our closed loop and open circuit system that runs down to the sump, we still had dead spots, just like you do in any reef tank. Just our problem to solve it required a lot more flow than you do at home. So we have placed throughout the rockwork, with the exception of this one that's on a bar, we have these AFC 150s.
By a biz.
That flow 30 to 40,000 gallons an hour. We're also currently using a Panther Ray, which is
the hydro tank right there in the center of the tank. Let's go to lighting.
Yeah, yep.
Come on, guys. And I'm just going to point them to you. There are 2 1,000 watters in the corner. Those are the square ones.
Those 1,000-watt LEDs are equivalent to approximately 5,000 or 6,000 watts of metal halide is how they equivalent.
And then all the other fixtures are the max spec 500 watters.
We wanted to keep the back wall of the tank dark so that it looked like it went deeper than it really is. And if we didn't light it, we thought we'd get that illusion, which seems to have worked out well. So most of our lighting is actually from the back forward, and then we have a little bit coming this way. We also chose different optic reflectors for the 500 watt units, whether it be a 120 degree spread or a 60 degree spread, depending on where they were pointed and how close to the glass they were. We were trying to minimize the overspill onto the glass so we didn't have to do the algae as much. And also in some of the spots where we needed to penetrate deeper, we used the 60 degree optics to penetrate deeper, while
The 120s give us a better wash of light over the portals and less of a hot spot. So there's a blend of 60s and 120s, more 60s on the outside so we don't get spill on the glass, and the downs are mostly 60s.
So we added a bunch of supplemental lights to these. Simple ones, let's talk about first. We did two of these massive 80-inch Reef Bright LEDs. There's two of them. You only see them at night and in romantic mode, but they do give a really nice ambiance to the end of the day. In addition, we've also added 4 Amazonas from Orphic. And then we gained confidence that this air condition back here was sufficient enough to go put some metal halides in. And we did that really to increase the bandwidth of light above and beyond the LED.
And the other thing to take note of back here is our lights are very close to the tank because of this being the first floor of the house above us. This was our height restriction. Had we had more space, we might have done things differently with the lights, because the further they are away, the more they would spill. But we needed to use more lights because we're closer to the actual thing, and they don't spill as much because we're closer. So it also traps a little more heat, but like Andrew said, the air conditioner is more than enough to keep up with it.
Jonathan, let's talk about this beautiful deck you made us.
So we're actually, being the tank goes 2 feet below grade, this is actually a hollow pit behind the tank that goes down 2 feet too, where we can connect to the closed loop penetrations that come out the back of the tank. Connect to each to a 6-inch header, one being a suction to the pump, and one being the supply to the pump, being the closed loop. And the valves are underneath this floor, where we can just pull up a little section and switch them from supply to return. They're actually 3-way valves. So throughout multiple spots of the aquarium, we have these Dectron dehumidifying air conditioning units, which, depending on the temperature, will actually just dehumidify and then reheat the air, or if the temperature is too high, they'll dehumidify like an air conditioner normally does and just put the cold air back into the room. It's all run through these PVC coated ducts so that we don't have any rust from a regular metal ductwork. The supply to the unit is underneath this grate, and this is the return cut out high that blows cool air on top of the tank.
Nice and cool.
We use a dose pump that supplies some bionic part 1, part 2 to the tank. We're actually doing in the neighborhood of about 4,000 mils a day of alkalinity, and similar in lines with the calcium.
Along with
Kalkwasser. And then when we talk about the sulfur reactor, we're also getting some, it's removing alkalinity, and then we're getting some back from it from the other part. All our ballasts are in a NEMA 4 enclosure, so that they don't get any humidity or a salt spray on them. It's not a chiller, but it's like an air exchanger, but it keeps the air separate. So the air inside of the hot air is circulated, it stays in there, but it goes against a transfer plate, which then takes cool air from the outside and cools that air, but outside air is never introduced into that box. We monitor the temperature of each ballast enclosure. So they're currently running at 98, 92
to 100.
And we have a fail-safe that if one of these heat exchangers was to fail and the ballast enclosure was to get too hot, the computer would shut down that bank of ballast and alert us that we have an over temperature situation, so we don't damage the ballast.
These massive boxes here control the big flow cannons. So this is from the Hydro Wizard, and the ones up here, 1, 2, 3, 4,
One behind it over here.
and one behind me here for the business. Got more to show you on the plumbing that runs through the lab. Jonathan, all yours.
So to get the water from the tank to the filter room, we had to run through about 70 feet of house. So while the house was being constructed, we built this trench that's approximately 3 or 4 feet deep by 5 feet wide to accommodate all of the pipes, which at this point have been taken over by some other trades as well now, so it's a good thing we have it. But in here we have the 2 main drains from the tank, the 2 supply and return for the closed loop, and the return back to the tank, as well as multiple electrical conduits that are run to the computer. From the back of the tank to not where the pipes stop, but to where the trench stops, it's about 70 feet. It's all concrete, and at one point it was open, and I'm sure at some point we'll post a picture of that for you guys to see. But currently we have just 2 access points, this being our main access point, which opens up to be about 8 feet by 4 feet, if we ever have to get in there, or add equipment or remove stuff. So we put our chiller down here, and we've used it for a bunch of other space that we ran out of for other equipment. But this runs through now what is the lab, and then it goes into the room with the protein skimmers, and we could follow the path of it if you guys would like. So from behind the tank, we run through the lab into the next room here, which Andrew will take us on a tour of, which is where a lot more equipment is, and it's also the path of these pipes.
It's part of our HVAC system, is actually in our house boiler system room, and we're going to take you in there, and Jonathan's going to explain to you the boilers and how they were plumbed. If you want some scuba suits to go in, you can also get some in here.
Good spot to dry it with all the heat from the boilers.
This is our heating source for the aquarium and all the water change tanks as well. These are 2 600,000 BTU boilers that
Loch Navar.
each one being 600,000 BTUs. Depending on how cold the water is coming back, they'll either one will turn on or they'll both run simultaneously if we need a higher heating demand. Each heating zone has its own circulator, which are these red pumps here that supply water to titanium heat exchangers. The copper pipe transitions to a polyethylene pipe. So we chose to go with polyethylene pipe once it left this room so that the corrosive saltwater air wouldn't oxidize or eat through the copper pipe. The polyethylene pipe is not affected by that. And the polyethylene pipe connects right to the titanium heat exchanger, and also returns the water back in polyethylene, and we convert it back to copper once we enter this room. Water change tank, the 5,000 gallon water change tank is the one we use primarily, and we get heat groundwater, which is approximately 55 degrees to the 75 degrees we need to use and make salt water in less than an hour.
So 5,000 gallons going
20
up
degrees.
20 degrees in really 30, 40 minutes.
Just to put this in perspective, we have 1.2 million BTUs for the fish tanks. An average house has 200,000 BTUs to heat the entire house.
This room, by the way, has 2 800 amp services coming in the house.
Electrical services.
So it's 1,600 amps of electrical service. That is probably, the average house probably has 200 to 400. So it's quite a bit more than your average house. Let's back out of this smoky room and into the filter room. Welcome to our skimmer, reactor, and filter room. Jonathan, you want to talk about the skimmers first?
First, I'll give an interesting bit of information.
Yep.
Might cut this out, but I really feel like these are Andrew's favorite pieces of equipment.
I love them. They're my twins.
His twins comes back here every day to look at his foam production.
I'm a foam junkie.
Yeah.
And by the way, there is a fine setting where if you run it too high, you don't get enough foam. You run it too low, you don't get enough foam. We just like it right where dry foam puddles over.
Little details about the skimmers is they are produced by MRC Life Support. They are 36 inches in diameter, each one, and approximately 9 feet tall. Each one is being supplied with about 150 gallons of water a minute to each skimmer, and there's 2 of them. They have their own needle wheel pump that runs on the base of them there, which gives us that real fine, thick foam. The one that's further back to the left is being supplied with ozone, which Andrew will give you some details about the amount of ozone we're using and how he's seen it work wonders for his water clarity.
Yeah, so if you come back here, we're using 2 halves of a Ozatec machine. Each is 1.2 grams or something like that, 1.3
I
grams.
think they're 1 gram without oxygen. They're probably close to 2 grams each with oxygen.
2 grams each.
Yeah,
with
we're running
oxygen.
pure oxygen into them from an oxygen concentrator.
Okay. And we have found we have not needed more than 1 on at a time. And the oxygen concentrator or air dryer is behind us in a closet in the lab.
That we have an ozone alarm in the bottom corner there. We also vent the skimmer cups to outside so that we're not releasing any of this into the air of this house where we could possibly be breathing it. The skimmers are actually connected to the house waistline, which goes out to the dry wells, which we'll talk about in a minute. And they all automatically wash themselves a couple times a day as well.
Even though the guys do a better job with the elbow grease and getting up there the ladder than the automatic washers.
We also monitor the waistline of the skimmers with a flow switch that if there's too much flow because the skimmers are overflowing, it'll actually shut down the corresponding skimmer.
So we don't empty out of something.
And then the other piece of equipment in this room from MRC is our sulfur reactor, a 7-foot tall chamber that contains the actual sulfur media, which is where the denitrification occurs. And during that process, we're left with a effluent that has a very low pH, and that travels into the second chamber, which is behind that, which contains aragonite media like a calcium reactor, and that lower pH water then dissolves that media and buffs the water back up from that process, which makes it safer for the aquarium, and then it flows back to the sump.
The amount of fish and food that we feed this tank, the nitrates would climb to the sky. This is the most efficient way in this little space to be able to reduce nitrates. The sulfur reactor is filled to about here. We run more or less 2 gallons per minute, nice and slow through it, reverse flow. And we want to have somewhere between 0 and 5 ppms of nitrate coming out of this reactor. The faster we run it, we get a potential stripping in the water, but you might get a nitrate of 5. You run it slower, you get a nitrate coming out of here 0, but it's slower reaction time with the water.
So here we have the sand filter, which is our primary mechanical filtration for the 17,000 gallon tank. It's 48 inches in diameter and holds 1,000 gallons of media, which we actually use a glass media so that it doesn't compact like some of the gravel medias do. It's connected to the computer, and it, instead of having to adjust the valves manually, one button press puts it into backwash mode and back into regular mode. The water exits the sand filter, and then it then goes through 2 titanium heat exchangers, which are for the chiller, and a 3rd titanium heat exchanger on the bottom here that's connected to the boilers for heating. We split up the chilling and heating like this, part in the main system, part in the open system. So God forbid we had a system go down, the tank is still operational, whether it be on the closed loop or the open system.
Well, I know you see another skimmer here and a bunch of empty reactors. This is for the 2,500 gallon system in our office that is up and running and will be the start of the next project. Let's go outside to the pit and see all the HVAC and generators for alternative power.
So we have twin 125 kW generators from Polo, 1 for each 800 amp service. These are the transfer switches for them, so that when we lose utility power, we automatically switch to these natural gas generators. It's almost a seamless transition.
I mean, they exercise every Monday, and the unique part of it is now they're on our main computer.
Yeah, our computer monitors them via Modbus, which is a communications protocol for any errors, low oil, water temperature, and things like that.
So no surprises during a storm.
And then the other equipment in this area is we have the 2 bigger units here are the 2 5-ton condensers for the closed loop chillers.
And the smaller one here is a 4-ton condenser for the chiller on the 2500 closed loop. On the top of the pit here, we have 2 more Dectron units, which are for different dehumidification in different areas of the house.
Tell us a little bit about why we did 2 on closed loop, 2 on the regulars, and the redundancy
So
there. And
we decided to go with smaller chillers and redundancy for 2 reasons. One is a power factor here to supply power to just one big 20-ton unit would be more of a challenge due to the electrical requirements of it. So with that, we decided to go with 4 smaller units for the 17,000-gallon tank, so that if one went down, we weren't losing all our chilling, and we put 2 on the closed loop and 2 on the main system, so that if we were to lose a pump and weren't able to run either the closed loop or the main system, we would still have chilling and heating, as well as the fact that if we ever had to drain the tank, we could still run it on the closed loop. It's shallow and still maintain the proper temperatures required.
a lot of redundancy there. Okay, this is the brains of the operation. We nicknamed Skynet. This is Jonathan's baby. So he will be speaking to you about this. But before we talk about it, I just want you to know that there are 4 people monitoring this remotely at all times, looking for warning signals, etc. It will send messages. It will even wake you up at home if you're not answering the messages.
So there's a tremendous amount going on in here. We have the PLC portion, which would be equivalent to like an Apex, but this is just more commercial automation, or for like factories and things like that. It's able to process data at a tremendous amount of speed. It actually scans all its sensors multiple times per second.
How many probes do they on this system? Running all the pipes and stuff.
Between flow sensors, temperature, all of those, you probably have 50, 60 probes in different locations with different applications. All the inputs are into here, and there's a brain, and there's actually 2 remote locations downstairs where there's actually separate standalone units that all relay their information back to here. So there's countless data points from that. We're also taking information from, like Andrew said, the generators and from the motor controls, which I'll explain in a second. We also monitor all the circuit breakers. So everything for the tank, with the exception of the condensers for the chillers, all are powered from this panel. Every light, every pump, every little thing comes from here. So all the power is distributed from here. We also have the network for all the communications within the fish tank is ran to here. All those remote locations, the touch screens, the HMIs, all come back to here. All the smaller motors, like on the calcium reactors and sulfur reactors, are controlled by these relays here. Bigger motors, being that they're 3-phase motors and we didn't have that available here, we're actually using a VFD to replicate that 3rd phase. The VFD takes regular household power and makes it into more of an industrial type application. It also is able to control the hertz at which the electric cycling, which therefore controls the speed at which the motor is spinning. So rather than turning a valve down, it can control the flow. We actually hit speed up or slow down each motor individually so that we can dial in the exact flow rate we're looking for. And in terms of like the sand filter or something that as it gets dirty, we're able to, keep a consistent flow rate with these devices as well. They also protect the motors thermally too, by if the motor is drawing too much energy, it will actually shut down to protect the motor. On the computer system here, we have a layout of all the piping and the equipment that's running. Here we have the sump level, which is approximately 1,787 gallons of water in the sump right now. The water is sucked out of the sump into the 3 pumps. 2 are running, 1 is not. That is the spare pump. Those then converge and feed 2 chillers that are on currently and a heater that is not. The water comes out of those, it mixes back into the mainstream and goes through the UV at 560 gallons a minute. is then supplied back to the main tank through the main pipe, as well as the two surge valves. The surge valves are red right now because they both happen to be closed at the time of filming this. We then also have the closed loop, which is drawing water from the tank back into a pump. We have one running and the backup there. We are then flowing through the sand filter, which has 27 psi of pressure in it, which we backwash it when it gets to approximately 30. So there's 144 gallons a minute going through the sand filter. The whole closed loop is running 182 right now. We're running a side stream with some water bypassing around the sand filter. The water that is filtered through the sand filter then goes through two chillers and a heater, which none of which are on at this current moment. All that water reconverges and returns back to the tank. While we're discussing this, you can see one of the surge valves open and it's now green. From the sump, we are also feeding the skimmer pump, which is then feeding each skimmer, left and right. We're running a little low now, but 102 gallons a minute. We also have an accessory pump, which is feeding the sulfur reactor, and it's feeding other reactors that aren't being monitored, such as the GFO and carbon. Here we have expanded views of all of those, as well as the ballast for the UVs, the ballast temperatures, the flow rates and temperatures through each chiller and heater. Here we have expanded version of the closed loop with the sand filter, the flow rate and temperatures through each one of those chillers and heaters, the bypass flow rate and temperature. Here we have the surge valves, one being open, one being closed. They're both in auto mode. We can also lock them to close where they won't do anything, and we can also lock them to open where they'll both be on. Like I said, they're running a subroutine that's random on and off times, and they start at 7 a.m. and run to noon. They take an hour break and they run from 1 o'clock to 6 p.m. and then they just automatically go to off so that there's a calming period in the tank. On the skimmer here, we have the main pump that's feeding the skimmers, each one running 100 gallons a minute now. Their individual needle wheel pumps are on. We have the abilities to shut those on and off. We have our washdown timers and duration of the washdown, as well as our ozone set point and levels. And if we wanted to run that ozone on a specific time frame, we could also do that too. If we didn't want to run it during the day or at night, we could adjust it that way as well. But now we're just relating it to ORP. We also have the lighting for all of the LEDs that are on this computer. Their ballast temperatures, whether it's in auto mode or manual mode. Each light has an on time and an off time and its intensity. With these units, LED units, the minimum intensity is 10% from the manufacturer.
Most important, our sump level. You never want that to go to 0. Low sump alert on your text is bad. To the RO.
This is an 8,000 gallon a day RO, which roughly is like 6 gallons a minute. I have to check my math on that. But, so, I mean, most household ROs are doing 75 gallons a day. So this is doing 6 gallons a minute.
Guys, this is our RO pressure. That's not our wastewater.
Consists of 4.5 inch by 40 inch membranes ran by a 1.5 horsepower booster pump. We have a 1 micron pre-filter and a 5 micron carbon block before that. And after the membranes, we then go through a cation, an anion, and a mixed bed DI resins. And these are approximately 10 inches by 60 inches, holding about 100 pounds of DI resin each.
And as long as we're over here, we make our evaporation every morning, which is roughly 45 gallons a day. We fill this bucket up with RO water daily, add about 1.5 cups of cork water to it, turn on our Sandler industrial pump, and this drips this water over 24 hours into the downstairs sump for additional calcium and alkalinity.
But what we're looking at over here is our UV for the main tank, which is 3,700 watts. It's a 14 inch in diameter, 7-foot long unit, 10 bulbs, 10 375 watt bulbs with an 8-inch inlet and an 8-inch outlet. We're currently flowing 600 gallons a minute through it, but the UV is sized to flow our maximum flow rate, which is 1,000 gallons a minute, and still have 275,000 microjoules of killing capacity, which is strong enough to kill almost every virus and pathogen that will flow through it, including ick and velvet. So at the lower flow rate, we're getting some sap and everything. The unit is controlled on the computer for inside temperature. If we were to lose flow rate or something was to happen, then if the water temperature gets 5 degrees hotter than the tank water, it will shut all the ballast off. There's also a flow switch in it, which if we lose flow rate, that it will shut the ballast off. And if that was to fail, there's a thermometer in it as well that's off of the computer that if it was to get too hot, will shut it down. So we have 3 fail safes to prevent it from overheating if we were to lose flow.
Hi, I'm Jonathan, and today we're going to be taking a tour of the sub-basement